Hello, my name is Jake Roggenbuck. I'm currently in ECS 170, and I'm working on the third and final project to train a deep Q network to play Pac-Man. I thought I'd journal some of the things that I've tried and some of the challenges I've faced during this project so that I remember it, and hopefully it might be useful to you. There's a lot of content that I needed to read and look up to understand how to make my network better. One of the papers that was pretty critical is a paper called the Rainbow paper in Q networks. What they try is a bunch of different techniques that had previously been reported individually and try combining them. And they realize that the effectiveness of all of the strategies combined far surpass any single one of them. And I took this inspiration for the extra credit part of this assignment. Really what was interesting in the extra credit portion was the stuff I did with a larger network. The network that we use is actually really quite small, so giving it a lot of extra power is very useful. The problem that we run into is with a larger network and a restricted amount of training steps is we're not allowed to learn that much during it. One thing that we're restricted is environment steps. This is how many times we could interact with the environment, but that doesn't mean we can't learn multiple times during a single environment interaction. What we could do is we could take one environment step, see what happens, and then move our gradient multiple times during that single training step. This definitely counts as one single training step, but we learn from it multiple different times. We want to make sure our gradient is as close as we can to what we think it should be during that step before moving on. This allows us to do a lot more of that learning in between different steps, and I think this was a pretty creative solution. Something else that I learned when playing around with the environment is this environment is for Atari games in general. And in a lot of Atari games, there's the up and right, or up and left, down and right moves. These moves are important in other games, but do not apply to Pac-Man. Which means we're trying a bunch of different moves, and we might think that down and right is the correct move some of the time, because when we try it, it seems to work. But it may be that we're already against a wall, and it's only performing the same thing as a normal left move or a normal right move. So removing these completely from our random steps and from our training made our model a lot more efficient, and that's the one that's currently running behind me. So I hope that with this, I'll get an even better score. My score previously topped out at 3680, which is a very high score compared to the one I started with. The initial part of this homework asks us to use the normal provided architecture and then change the hyperparameters and then add certain parts during the training loop. We're limited to 500,000 training steps, which is certainly enough to get over the benchmark of a 500 game score. To get full credit on this assignment, we need to get 750 points. Mine was able to easily hit the roughly 1,000 benchmark. I graphed a line through 500 and then 750 just to know where those are compared to what the score I got was. One really interesting thing about this project is we could replay the environment from one of the games to see how the agent performed. So I could overlay a video of our agent running on one of the games that it did particularly well at. Something that I found quite tricky is once we trained the model and we actually got it to play the best game, oftentimes it would play less than a best game. So running it multiple times was important. I still am not exactly sure why this is the case, but I'll be looking into that further because some of the best scores are hidden just in the fact that I haven't rerun this code multiple times to see why it's not doing that. But it is the model and it is trying to find the best score. It just sometimes does not. Something else that was really important was the loss function. We're told, or recommended at least, to use a quadratic loss. That is the target minus the observed, and then you square that and then sum those up over the examples you have to get the loss. I chose something that was a bit smoother of a function. I was experimenting with a bunch of different ones and found that this one performed the best. A lot of this assignment was trial and error. With the student subscription, we get something like 100 compute credits, and I burned through all those and then bought 100 more, but it was very worthwhile to train on a G4 GPU Python instance instead of having to use a local machine or CPU. This made it really easy to try a bunch of things, have it run for 15 to 30 minutes in the Copilot notebook, and see what the results were rather than having to guess. Oftentimes I would stop it early because I saw that the trajectory was not good enough and that I wanted to change something. There was a few other optimizations that I went for. You can decide to update the weights on the target network from the network that you're using during running to you'll update it occasionally just so that you have a baseline and that your strategy stays consistent. If you were to change it, it would be a changing target where you wouldn't know exactly how to perform. You want some continuity for what is scored well and what is scored poorly when you're training. Something unexpected that I immediately noticed was most of the time when I train machine learning projects, I see the loss go down. This isn't the case for Q-learning. Loss can go down and then back up again. And that's indicative of it finding a different strategy and then not being as good at that strategy as it was the previous strategy, but still performing better. So one of the first models I trained, the loss went down as expected and then shot up. And I was really concerned that something was very, very wrong because my loss didn't converge. But in fact, for Q networks, that doesn't need to be the case. It's just finding more strategies. Some recommendations I have about this project that are about logistics is make sure to constantly save your notebook and then probably use something like Git to check it in. Because oftentimes I would run something, it would score better, I'd change something, it would not run as good, and then I wouldn't have the original code. Colab does have the ability for revisions and version history, but it isn't the same as checking something into Git, saying that this is my final model, this is my final notebook, here's an image of it, here's the score it got, save it as a commit, be able to revert completely later. That's something that's really critical here. This homework is actually very challenging. It took me the entire first week to understand what I was doing, then realize I had read some of the rules wrong and I had to start from scratch. This isn't a completely start over. I had learned a lot about Q networks and exactly what I had to do. So the second time it only took me a day or two, which is quite nice. But it was really important that I started early, especially because of the compute credits. One thing that you definitely have to do is sign up for the student compute credits because the free model is simply not enough. Your models will train for an hour and a half when they could be training for 15 minutes. This is not going to help you do quick iteration. It's going to take you so much longer to do this homework. Something that I noticed initially was the graph for performance was not as helpful as you might want it to be. It's a very good way to check that a model is at least working or check for the best score, right? We monitor that red line for the moving average, 20 game average, and we take the maximum of that and see if that qualifies you for the first part of it. The problem is that this is not a very good diagnostic graph. What you should be doing is adding a lot of extra graphs to see what the model is actually doing, to see ways that you could improve it. There's a lot of information that is not on the table that you totally could have on the table to be able to learn from. Something else I built was a progress bar. This is totally not necessary, but for me at least, it was very interesting to have something show a lot more information than would be normally. Something else that I found was really interesting is you could play around with batch size. The batch size initially at least is very, very small. This is something that I recommend trying out, especially if you have good compute and it won't take very long. Something that's not set by default in the starter program is having a delay between when you start training and then when you actually start pulling from the memory. Something about the memory that I think is really important is you actually want some diversity in your memory inside your buffer before you actually start making some strong predictions based on it. So I actually don't even start learning until it's gone through a lot of environmental steps to actually have some diverse buffer of information we could take to. Otherwise, it might be too skewed towards certain types of actions initially. This and experimenting with the learning rate is pretty important. There's a lot of examples of if you have your learning rate set too high, it'll miss the minimum value when converging to a gradient and it will skip over it. This is something that's kind of a big problem. It will look like an unstable prediction, but you actually want it to be definitely slowing down at some point, which is why different optimizers are very good to experiment with. You can use momentum to slow down your learning at the very end once it's certain that you're trying to learn a very specific target rather than generally find the deepest holes in the gradient plane. For me, this looked like just using AdamW and setting an ability for momentum to slow down at some point. The biggest problem here is why don't you just have the momentum set low to begin with? And this is a very interesting idea, but the problem is we're limited on training steps, so this is also a problem. You can fix this by learning multiple times during one environment step, which is what I do, but even this is not enough to really compensate for a learning rate that's way too small. That being said, I do reduce the learning rate quite a bit in this project. Thank you for listening. I'm gonna now go and train this for another few hours, and I'll let you know what the results are.